When we specify something like a 95% value at risk or 95% VaR, what we mean is that 95% is the confidence level and therefore 5% is the significance level, and that means we expect on 5% of days for the actual loss to be worse than the VaR or to exceed the VaR. This video is about the back test of a VaR, which is a very handy statistical tool that we have at our disposal to back test or to test the validity of this model. The back test will allow us to make a decision as to whether to accept this as a good VaR model or to reject it as a VaR model. But it's just a statistical hypothesis test, meaning we are going to face an inevitable trade-off between a type 1 and type 2 error, which is to say we can't avoid this tension between making a mistake of rejecting a good VaR model and the other kind of mistake of accepting a bad VaR model. So now I'd like to illustrate this with some examples, including a couple of charts that I've replicated from Philip Jorian's Chapter 6, Assigned to FRM Candidates. In order to understand the VaR backtest, we need to understand the key metric that we look at, and that's called the number of exceptions. It has a fancier name. It's also called the number of exceedances. And the number of exceptions is a simple idea. We look back over the historical window and we count the number of days on which the actual loss was worse than our VaR, or the number of days on which the actual loss exceeded the VaR. So just to illustrate exactly how that works, I have a simple simulation here going down in one column. You can see number of days, and it goes way down the spreadsheet to 250 trading days. So we're looking back over 1 year, and then I've just generated a daily P&L according to these assumptions. I've randomized a mean of 2 and a volatility of 5. So if we have this sort of random variable on a daily basis, and we wanted to perfectly calibrate a 95% VaR, well, then we would do that by saying negative the mu plus the volatility multiplied by, I would use norm SINV, and then my confidence level for the VaR, which is 95%. So we get 6.22, and in typical risk fashion, I've expressed what is mathematically a negative 6.22, a loss as a positive. So our VaR of 6.22, it's the 95% VaR. What that means is that on 5% of days, we expect the loss to exceed the VaR, or mathematically, to be worse than negative 6.22. So in this simulation, I'm not showing any, but here's another simulation. You can see where on day 3 of my random simulation, if I look back, there was a loss of 7.2, let's say the daily loss of $7.2 million. And that is worse than the VaR, so it exceeds the VaR, and you'll notice I've counted it as an exception or exceedance. And then we go to day 4, or going back T-4 if you like. The profit and loss was positive 6.3. That obviously is not worse than the VaR, so I count a 0. And then here on day 7, we had another loss that is worse than the VaR. So going down all 250, this cell simply counts the sum. And in this particular random simulation, or this particular trial, there were 15 exceptions. In other words, over the past year of 250 trading days, we happened to observe a loss that's worse than the VaR, and that is 6% of the 250. Now we get, this is the essence of the back test. If we actually observe this, you'll notice that 95% VaR, how many do we actually expect? Well, if it's a perfectly accurate model, we expect 5% multiplied by 250, or 12.5 exceptions, would have given us exactly 5%. We had 15 exceptions, or 6%, which even without doing any formal statistics, it intuitively looks pretty close to our 5%, and we would probably accept that for this sample size, we're going to accept the idea that this is a good VaR model, meaning it's well calibrated, or statistically we'll see that what we're doing is we are failing to reject the null hypothesis that this is a good VaR model. And so this is the essence of the backtest. And for example, knowing that this would be the ideal VaR, 95% VaR for 95% VaR under these assumptions, we can see that if we set the VaR to 2, that is too low. And the point of the backtest would be to expose that. And you can see here, if our actual VaR is 2, there are 64 exceptions, 25.6 of the sample size. That's way off from the 5%. Again, we expect the percentage of exceptions to be equal to the significance level of our VaR, 1 minus the confidence. And so this would immediately, under almost any scenario I run here, our backtest would expose that our VaR is far too low. On the other hand, if we set it up to 10, you can see we can go a long time before finding exceptions, and we're not observing anywhere near the 5% of exceptions that we expect. And so that is the essence of the VaR backtest, and perhaps you've anticipated the distribution that characterizes this backtest, because for each day we have a simple yes or no. Was it exceeded? No. Was it exceeded? No. Was it exceeded? Yes. These are Bernoulli variables, and we only need to make really one key but vital assumption to treat this series of Bernoullis as a binomial. So under this backtest, we characterize the backtest with a binomial. After all, this is just a sequence of Bernoullis. But of course, you probably know key assumption, we see this over and over again, is IID. So we do treat this as a binomial, but we're making the assumption of IID, meaning each day is identical, but perhaps more important, each day is independent. So realistically, we know it's often the case that the exceptions do cluster, which would be a violation of one of these I's, the independence. And if we want to really be good about it, we need to move to more sophisticated back tests, which are available, and I'm not covering here. Now, I've illustrated here the histogram for this presumed binomial distribution, and now I've just shifted to the only change here. We'll have two changes, because I'm going to start following what's in Jorian Chapter 6 for FRM candidates. And starting here, so I'm changing now to a 99% VaR model. Again, what does that mean? That means for the VaR level, we expect exceptions on 1% of days. On 1% of days, we expect the VaR to be worse than our VaR level. And so if there are 500 days, so that would be 2 days, 2 years, where each year is 250 days, then we can characterize this with a binomial conditional on a correct VaR model and our IID assumption, of course, right? It's important to keep in mind it's conditional on a correct model. If we have a correct VaR model, a 99% VaR, the probability of an exception on a given of an exception or on a given day is 1%, and for t equals 500, here is the distribution. And then as far as the statistical back test, which is really a hypothesis test or significance test, the null hypothesis is that we have a good model. And for 500 days, this binomial has a mean of 1% multiplied by 500, or 5 days. So that's right here, pretty much in the middle, is 5 exceptions. In other words, if we look back over 2 years, and we happen to observe 5 exceptions for our 99% VaR model, that's pretty much exactly what we expect. And so we would accept this as a good model, or statistically we would fail to reject the null hypothesis that this is a good model. But over 500 days, if we observe 4 or 6, maybe even 3 or 7, think intuitively we can understand that we might also be inclined to accept this as a good 99% model, even if the number of exceptions isn't exactly what we expect, because sampling, we know that there is such a thing as sampling variation. However, if we look back over 500 days, for example, and if we observe 0 exceptions under a valid binomial, if this were a good VaR model, the probability of 0 exceptions, and you can see I'm just using a straight binomial distribution, is only 0.7%. So, for example, if we wanted to conduct this back test with a 95% two-sided confidence interval, you can see 0.7% is too low. It's going to be in the rejection region. So that's why I have it in red. We observe 0, and we would, under a 95% confidence, reject the null hypothesis that this is a good model. In other words, we would decide this is a bad model. At the same time, we know statistically we can see that it is possible to make a mistake here, because this, after all, is the distribution for a good model. And so here we would in fact be committing a type 1 error. We would be rejecting a true null hypothesis, and we could make that mistake on the other side as well. So now the only change I'm going to make here is reduce the number of days in the window to 250. So now we go back to a 1-year look, and my reason for doing that is that this matches the chart that's in Jorian Chapter 6 for FRM candidates. So only thing here is that the sample size has been reduced. Notice something interesting about 0 exceptions. If we only look back over a year, the probability of 0 exceptions under a correct 99% VaR model is fully 8.11%. And that means that if we select a 95% or 99% confidence interval for our back test, this will not be in the rejection region. So notice this moves into the acceptance regions. If we observe 0, it's close enough to what we expect, the mean here, which is 2.5, 1% times 250. 0 is close enough that we would accept this as a good model. So 0 presents an interesting philosophical dilemma, because if we look back over a year and observe 0 exceptions, intuitively think our VaR must be set too high. What Jorian shows here is the rejection region where we've selected a cutoff. But I want to just say one thing before I address that, which is implicit in the last 2 sheets. And that is, I'm raising this because it's a common confusion when we first introduce this to new learners. You will have noticed, and that is to say, you will have noticed there are 2 confidence levels at play here in the back test. Here I have a 99% VaR model. And we know what that means, right? That means on 1% of days, we do expect the actual loss to exceed the VaR. But then when we go back and we back test it, we select the confidence level of our back test. This could be 99%, but there's no reason for it to necessarily be 99%. We could conduct a 95% confidence back test of the 99% VaR. I actually think if you're with me on that concept, you're far along, because this is probably the most common initial stumbling block. The fact that we have a VaR and then the back test is its own significance test. There's one more thing about that. This VaR is always one-tailed. This confidence test could be like any statistical, this back test, like any statistical test, could be 1 or 2-sided. So go back to Jorian's here. Then he illustrates where we have selected a cutoff. The selection, there's nothing magic or necessary about any particular cutoff. Jorian happens to select the cutoff here at 5 or greater. The cutoff necessarily involves the classical statistical trade-off between which error we're more afraid of making, the type 1 or type 2 error. He shows a cutoff of 5 or greater, which simply means that if we observe here over the last 250 days, the number of exceptions to be 5 or greater, we're going to reject the null, and therefore we're going to decide this is a bad model. Here, under a 5 or more cutoff, you can see Just the odds of a 5 is fully 6.7%, so it's quite plausible to make this type 1 error. And in fact, we can quantify here. I can just say equals 1 minus binomial distribution. I'm going to say 4 over 250 trials. Probability is 1%. Cumulative is true. 10.8%, in other words, I just did 1 minus everything that's 4 or less. So I've quantified the total probability of everything to the right, including this tail, which gets very tiny here over to the right. And that's why in the actual chart in his book, he says if the cutoff is 5, the probability of a type 1 error equals 10.8%. And it's important to keep in mind that is conditional on the model being correct, this distribution. Then he shows an incorrect model, right? We conduct the back test because we don't know a priori if the model is correct or not. He then illustrates an incorrect model, and here's where we get challenged. What incorrect model? There is only one correct 99% VaR model, but there are almost an infinite number of incorrect models. He shows an incorrect model of, you can see here, probably 3%, meaning this is the distribution if the actual VaR is 97%. And this is illustrating the situation where we think we have a 99% VaR, but the actual VaR is 97, meaning we've set it too low. And again, our cutoff is 5 or more. And these are now blue, meaning that if we observe, for example, 6 or 7 or 8, we don't know the VaR is 97, but these are actually quite near the middle of the distribution. These are greater than our cutoff. We're going to reject here, but it is an incorrect model. So these are blue because we're making a correct decision. Our cutoff is 5 or more, meaning if we observe, let's say, 3 exceptions, we are going to accept this model, but it's an incorrect model. And so here we've committed a type 2 error, right? We have accepted a false null hypothesis. In other words, we have decided the model is good, but actually the model is bad. And he quantifies this by summing these values here. And the total of these, I think it's 12.8%. If I look at my summation here, yeah, 12.8%. So the probability of a type 2 error then becomes 12.8% in this. In this case, though, it's conditional on it being this kind of correct model. That's why I show here what's not in Jorian, just to illustrate this inevitable challenge. It reminds me of Tolstoy said, all happy families are happy alike, or I'm mangling this, but all happy families are happy in similar ways, but unhappy families are unhappy in different ways. Well, our correct 99% model only has one distribution. If we think we have a 99% VaR, but it's incorrect, it can be incorrect in many ways. And so here I just illustrate, here would be, it's incorrect because it's actually 98%, here it's actually 97, here it's actually 96, here it's actually 95. So I suppose as we go left to right, it's getting incorrect in increasingly worse ways. And then I'm showing here just simply the corresponding binomial distribution to illustrate the challenge of specifying the probability of our type 2 error when we don't really know how incorrect the model could be. Which leads me finally, this is also not in Jorian, but which brings this together here into what is essentially a trade-off. Obviously, this back test is a very helpful test of helping us determine whether the VaR model is correct or incorrect. But the selection of the cutoff involves a necessary trade-off The easiest way to mitigate this trade-off is to increase the sample size. But here I have repeated again the binomial distribution for 250 trading days. And here, Jorian's illustrated selection of a cutoff that's 5 or greater. And so that is right here. I'll color that a little. And so we have seen that if that model, if our 99% VaR is correct and we cut off at 5 or more, we have fully a 10.8% probability of committing a type 1 error. That is to say, ending up in here, rejecting a VaR model that was actually good. And we also have, you can see here, various probabilities to illustrate the probability of committing a type 2 error, which is to say, which would be to accept a VaR model. Now, you might agree with me intuitively that it's easy to imagine that the consequences or costs of these mistakes, each of these mistakes, are not identical. We may believe that it's more serious, more costly to us to commit the type 2 error. That is to say, it's more serious to accept a bad model. And so we may want to decrease the probability of committing a type 2 error. You can see a way to do that is just to move the cutoff here to the left. So now we'll draw the cutoff at 4. And you can see this will decrease the probability of our committing a type 2 error. But in moving the cutoff to the left, you can see we've dramatically increased the probability of a type 1 error or rejecting a good model. On the other hand, we can move the cutoff here higher, which will necessarily decrease the probability of committing a type 1 error, but depending on the incorrectness, but directionally in all cases, will increase the probability of committing a type 2 error. So this is the inevitable, unavoidable trade-off in the backtest, which does not invalidate the backtest, but just is something we need to use going along in using the backtest. We always want to be in mind these probabilities are conditional on the assumption that the model is correct. So if that's helpful, please subscribe to the channel and you'll get notified of my next video. Thank you.